Hello, you absolute legends. Consider the following situation. We have a peptide hormone that is dissolved in solution, and we are going to measure the osmotic pressure to try to determine the grams per mole of that peptide hormone. Step one, read the question. The osmotic pressure of a peptide hormone solution containing 10.4 grams per liter is 0.3 atm at 25 degrees centigrade. Assuming ideal solution behavior, what is the peptide hormone's molecular weight? And as a added challenge, can you search which peptide hormone we're talking about? Peptide hormones, we've read the question aloud, and I've created a shopping list of every number that contains a unit meter. This peptide hormone solution, so hormone is referring to the biological effects it has on humans or mammals. Peptide is referring to the molecular structure of this complex. Peptide, protein. These little squiggles are meant to represent thousands, tens, or hundreds thousands of atoms. Peptides or proteins can be, we could have 5 amino acids in a row, like 80 atoms, or we could have 8,000 atoms when we're talking about the word peptide. So it's pretty vague in its size, but it means just hundreds at least. The molecular weight of anything is grams divided by moles. Okay, now, here's what I think is fascinating. We don't need a periodic table to get the molecular weight of this compound. Like, for months in chemistry, that's what we do. What's the molecular weight of CO2? Look it up on the periodic table. 1 carbon, 2 oxygens. Add them up, grams per mole. Not now. Now we have experiment. We make a solution of 10.4 grams of this unknown, isolated, purified peptide hormone in 1 liter of aqueous solution water. So I just have a blue line. In the atomic vision, I don't have water molecules drawn, but there's like, if this is representative of tens of thousands of atoms, there's millions and millions and millions of water molecules, crowding them around there. The pressure measured by an instrument in the laboratory and the temperature. Well, I need a final answer in grams on the numerator, so I'm going to start with this right here. 1 point. G. It's a terrible G. It's a better, but it's still a terrible G. That's a better G. This is a number with the unit that I'm looking for, grams on top. So I'm going to cross that off my shopping list because I've already used it once right here. I need moles in the bottom. I got nothing else that has moles in here. Okay? Now, the keystone from here on is that we are measuring the pressure of a solution in ATMs. This should remind us of gas stuff, hopefully, and B, the the kinetic motion of gases in solutions can be described with similar ways. The chaotic motion, the always moving, the always tumbling behavior of gases, we can also describe solutions with. So the gas constant, R, can snuggle up into our scaffold and help us set up things. The gas constant, R, ooh, man, it's a doozy mouthful, but it contains so much good stuff. Like, it's got 4 units in there. And I placed this gas constant in here just so I could get grams on top and moles on the bottom. And now I got to get rid of all this other ugly stuff. Oh, look at that. This is nice. Boom. 1 done. So that's not a coincidence that grams set up, that's not a coincidence that this set up the same way that we want our answer in, and that this cancels out that like top, cancels out bottom, that pattern. Pressure, pressure, we got that guy right there, easy. From our shopping list, 0.30 ATM. And also in our shopping list, we're told the temperature. We have to do a little conversion of Kelvin to Celsius. So 273 plus 25, 298 Kelvin. I've used everything in my shopping list. That's a good sign. Everything is canceled out of my scaffold except for what I need my answer in. So now I can pick up my calculator and calculate the molecular weight of this peptide hormone. Can you Google and make a guess of, or one of two, of what it could be? I hope this helps. Thank you.